All right, just so for this last section, it's going to be kind of a wrap up of the previous 3 introductions on these different types of identities. And so because this is likely to be a final exam problem, and it's a pretty typical problem for this course, what I want to go over is strategies for proving these trigonometric identities and different ones that you might encounter. So we'll just work through a problem and then I'll go through the strategies on the left as we do this. So we've got this this big trig identity here that we want to prove. I'm going to start by separating it into my left side and my right side. And the reason why I put the first one as 0 is because it's nice if you notice that immediately, but you don't necessarily ever have to use these identities if you do step 1, which is turn everything into sine and cosine. So that's what I'm going to do first, is apply step 1 over here on the right to that 2 secant x. And that's going to allow me to write that as 2 over cos x. So now everything's in sine and cosine. So we're pretty good there. Step 2 says simplify any negative angles. So I do have a couple of those on the left there. So I can tackle these. And so that's going to become cos x on the top over 1 minus sine x on the bottom, and then plus 1 minus sine x over cos x. And step 3 says combine all fractions. So that's definitely what I have here is 2 separated fractions. So I'm going to combine these over the common denominator of just the product of the bottom. So cos x times 1 minus sine x. There's no simpler thing that both of those terms go into. So that'll be step 3. And so I will have cos x times cos x. So it'll be cos squared x times actually plus 1 minus sine x squared over cos x 1 minus sine x, right? So just multiplied the cos by, we need another cos on the denominator, and then the second term needs another 1 minus sine x on the denominator. And so now what I'm going to do is just use some algebra to simplify this. So it's not really one of the steps, but it's something we should probably do every chance we get. So I'm going to simplify, and so I'll get cos squared x plus 1 minus 2 sine x plus sine squared x, and then over cos x 1 minus sine x. And then now, yeah, that's about as simple as I can get. And then what I'm looking for is now step 4. So now hopefully you can see what we've got here. I've got cos squared x plus sine squared x. That's 1. That is my Pythagorean identity. And so now if I actually apply step 4, what I'll get here is 2 minus 2 sine x over cos x 1 minus sine x. And hopefully you can see now the top and the bottom will have some cancellation if I just actually factor the 2. Again, that's part of simplifying. Usually when we have rationals, we want things factored over cos x 1 minus sine x. I've got some cancellation there. The 1 minus sine x is cancel. And what I'm left with is 2 over cos x, which is my right side. So that is how we would prove this particular identity. So let's try another. Anyway, so for B, this actually is really similar to one that I'd done in a different video. But that's okay. We're going to do this one with a different approach. So if you're paying attention to step 0, you might see that, there's that 1 plus cotan squared. That can be written as cosecant. But I'm not going to do that. I'm going to pretend that you forgot to look for that and show you how it still works out. So my left side is sine squared theta, 1 plus cot squared theta. My right side is 1. I'm not going to be working with the right side because it's already as simple as possible. And so I'm going to start by rewriting that cotan in sine and cos. So that's going to be sine squared theta, and that will be 1 plus cos squared theta over sine squared theta. So hopefully you kind of see what's happening here. I don't have step 2 at all. I don't have any negative angles. I could combine the fractions for 3, but what I might want to do before then is, so when I say combine fractions, I could combine the 1 into that fraction term. We can avoid that though. Instead, if you actually notice, if we distribute the sine squared, it's going to clean it up a little bit faster for us. So I'll just do some simplification first. That's going to give us sine squared theta plus cos squared theta. And then from there, I don't have anything for step 2. I now don't have anything for step 3. I definitely have 4. Sine squared theta plus cos squared theta is 1. That's my Pythagorean identity. So sorry, I actually should put that down here. And so I've got the right side. So it still works out. So even if you forget to use that identity, you can just avoid it by working with sines and cosines. All right, let's go with 2 more. All right, so for this one, C, what you can see is a whole bunch of 2x's inside of all of the trig expressions. But notice that they're all 2x, so they're actually all the same thing. We can just pretend that this is our theta. In fact, we could even, if you wanted, you could just go through and swap out theta equals 2x if you like. You can actually just say, let theta be 2x and then prove it for theta. That's completely fine. But we're just going to treat that 2x like its own little inside variable. We will learn formulas for dealing with 2 times something inside of trig later, but we're not there yet and we don't need it because they're all 2x. So we're actually pretty good when all of the insides are the same. So I'm going to jump right into step 1. I'm going to write everything with cosine and sine. So cotan is going to become cos 2x over sine 2x. Right, so that inside of 2x, that angle goes into both of those functions. And those are both squares. And cos is going to stay the same. Sine is not going to change, and cosecant, oh, you know what I forgot was to rewrite my left side and my right side, and I almost just did something that didn't make sense, so I'm going to switch that up. Right side is going to be cosecant 1 over sine squared. 2x. Okay, there we go. And so what I'm going to want to do now, I don't have any negative angles, and still all of the angles are the same. But what I can do now is combine all the fractions. So what I'm going to do is combine the left side over sine squared. So I will get cos squared 2x plus, well, let's say maybe you've noticed something else, but let's say we're going to go about this completely wrong here. Cos squared 2x plus sine squared 2x cos squared 2x plus sine 4 2x over sine squared 2x. Okay, so I certainly wasn't paying attention to the last step when I went ahead with this one, but this is good because I think most of you are just going to plow ahead with these rules that I've given you. So obviously the top does not look like 1. I do want the top to look like 1, so there's going to have to be some simplifications that get made to get that thing that I need on the right side. So we need equals 1. To me, that screams Pythagorean identity. That's probably what we're going to use here. So you might backtrack and notice that we have a cos squared plus sine squared. That should have been 1 right there. If you didn't notice that, there's other things that can be done, but I would just call your attention to this right here. So if I rewrite what I actually had there, I'm just gonna use that to factor this term right here, because I notice that from those two terms, I can pull that sine squared out that I just wrote. So sometimes you'll have to do little bits of backtracking here. You might go forward with something that makes your life harder. So just look back. Sometimes that's helpful. So if I actually do the backtrack here, I'm going to refactor that cos squared. And then hopefully notice here that this is my Pythagorean identity. This is equal to 1. It doesn't matter that the insides are 2x, the insides are the same. It doesn't matter what's on the inside. So that is going to be 1. So this is an application of the Pythagorean identity. I'm going to get equals cos squared 2x plus sine squared 2x times 1 over sine squared 2x. But now you should hopefully be seeing we have the exact same thing again, cos squared 2x plus sine squared 2x. This is also equal to 1. So by another application of that Pythagorean identity, I have now 1 over sine squared 2x, and that's my right side. So you might do things that are not totally helpful at first, but you can always just try to focus on what it is that you're trying to get at the end of the day, like what you want this thing to look like. I knew I needed a 1 on the top for these things to be equal. So I needed to look for ways to use this Pythagorean identity to mash it down to a 1 somehow. All right, and so one last one, we're going to do D here. We're going to show that 1 minus cos x equals 1 plus sine squared x over 1 plus cos x. So I'll get my left side and my right side. I definitely don't see any of case 0 there. Everything is already in sine and cosine. There's no negative angles. There's no fractions to combine. And now I'm actually getting a little bit worried here. I don't really see anywhere where I could get these variations of cos squared plus sine squared x equals 1. And I certainly can't do anything to simplify. So the question is, what do I do now? So there's one more thing that I'm going to add to this list. And if you're completely out of luck and stuck and like nothing else seems to be working here, we're going to use conjugates. So just like when you're trying to rationalize a denominator, conjugates are going to do something really nice for us. So like if you have 1 plus or minus cos x, you're probably going to try to use the opposite of that. So 1 minus or plus cos x. Right, the sign in the middle we want to flip over. And then the same thing with sine. We want that sign in the middle to change from a plus to a minus or a minus to a plus. So for this one here, I can see along the bottom, I've got this 1 plus cos x. So what I'm going to do here is multiply by the conjugate. And so the conjugate is just going to flip the sign in the middle. And when I say multiply by, because we're just dealing with an expression, what I'm going to have to do here is multiply the top and the bottom by the conjugate so that I'm multiplying by 1. And so what that's going to do for me, I'm going to leave the top factored. Now along the bottom, if I actually do that multiplication, it's a difference of squares. So I get 1 minus cos squared x. And then now I get to use the Pythagorean identity. Because now if I rearrange this, I have 1 minus cos squared x equals sine squared x. Or 1 minus cos squared theta, say, if I want to be consistent with what I'm using there. So yeah, so if I just rearrange that, the bottom is actually just sine squared. And so I can rewrite that as sine squared x times 1 minus cos x over sine squared x. They cancel. I get my 1 minus cos x. That's my left side. And so I'm done. That's about as hard as I get. That's the hardest trick that you'll ever encounter is recognizing that conjugate. It's reasonably common, so hopefully you'll get some practice with it. Yeah, so just for your own records, for when during the final, you're going to have to hand one of these things in. I will, on the question, say please refer to the video or the notes for how these solutions should look. The one thing I can say, though, more than anything, is show a lot of steps and a lot of work and explain what you're doing, as you're manipulating these things a little bit different than traditional equations. So you go from one step to the next, and they don't look the same. They don't look like basic algebra. So I need some little explanations along the way to see what's actually happening here. But that should be the gist for an intro for these. We'll get some more practice in the last section, 4.8. But this is something you're going to have to do on the final exam.